Okay, so I think we're done now. We sort of, this marks, or before the start of this lecture, I think this marks exactly 1/3 of the class. Right, so we're done with 1/3 of the class. Right, and basically this will now do, and one of the big things in complex analysis is definitely integration and Cauchy's theorem and some of its implications. And so we're actually going to start this next week. Right, so today I'm going to finish up talking a little bit about conformal mappings, and then we'll start with integration next week. Right, and sort of a lot of the cool, surprising things in complex analysis will all start showing up next week. Right? But we still have just a little bit of setup to do before we get there. And actually today it's not just setup. We're going to talk about conformal mappings, which are something quite interesting just by itself. Okay, so we saw at the end of the last lecture, right, and actually is in the homework too, or parts of it. Part of it we saw in the last lecture, and part of it was in the homework, right, that if I have a function f, right, from a region to the complex numbers, okay, so let's say this is a region. So by region, I mean that it's open and connected, right? It's like the nicest place to define functions on. Right, and f is differentiable, right, and f of z exists for all z in right. F of z exists and is 0 for all z in the region. Right, then f. Right, then f is constant. Right, and this was right. The important thing here is that the set is connected, and so because the set is connected, you can connect it by a line, by a polygon line, and then because the derivative is 0, it needs to be constant on each polygon line, and you immediately recover this. Right, but sort of maybe a bit more surprising is that the same is true for the real part of an analytic function, right? So if f is analytic, maybe I should write f analytic, just if f analytic, just to make it, right, analytic. Right, so if f is analytic, the same is true for the real part, the imaginary part, the argument, the modulos. Right, so if all basically you show, this was part of the homework, that if all these functions have have 0 derivative, then actually the whole function f needs to be constant, right? And we saw a version of this back in the beginning of the course when I said that if we had a function that took value only over the reals and was analytic, then the function needed to be constant, right? And these are just basically the same thing, right? If the imaginary part is 0, it's basically, if the imaginary part is constant, is up to a translation of function that's real. This is just the same thing for the complex, and the argument and the modulos are a little bit different, but it's a very nice exercise, and so this is in the homework. Right, but this shows why sort of the definition of region is in a way the right one, right? Because if we have a point, we have always a ball around it, so we can talk about derivatives and limits and so on. And it's very important for this to hold, for the region to be connected, right? If I have a set that's not connected, it could have derivative 0. It could just be one value in one of the connected components and another value in the other connected component, right? There's a priori no contradiction with that happening. And so in order to make have arguments that go from the derivative to saying something about the function, like the derivative being 0 to the function being being constant, it's really important that the set in which we're working is connected, right? So this is just to illustrate that. Okay, so now we'll talk a little bit about conformal mappings. Okay, so I won't define a conformal mapping yet, but let's just sort of investigate a little what goes on. If we think of a function f as a mapping, right? So we can think of a function f going from a region right, to say the complex, we're going to think of it as a mapping, right? What I mean by this, I mean a mapping and a function is the same. What I mean by this is we're going to try and understand what happens to the geometry, right? If you think of omega as a set with its geometry where you can draw lines and circles and make drawings and whatever you want to do, then we can push whatever drawing you made through the function, right? Whatever geometric property, you push it through the function and you try to understand what it looks like here, right? And this should tell you how the function is sort of transforming the space, right? And might even give you a lot of information both about the function and the geometry of each one of these domains. Let's say the function doesn't necessarily need to have its image be the all of C, right? Okay, so let's take an arc, right? Let's see what happens when we push an arc, right? If we push a line, say we have a line gamma, and we push it through a function f, right? Maybe we'll give some other line, right? F of gamma, right? If the function is continuous, right, we expect that, right, a line will go essentially to a line here, but let's try to understand a bit better what's going on here, okay? So let's say we take an arc gamma, right, and we take it to be, parameterized zt, let's say for t in some interval, right, alpha and beta. Okay, so it's some closed compact line. Okay, and let's say that f is continuous. Okay, in fact, we're going to ask that it's analytic, but for now, let's say it's continuous. Right, then we want to understand something about the image of the arc. Right? Through, right, when we apply f. Right, and so in particular, we can define a new arc, right, omega t, which is basically just f of the earlier arc. Right? This would be, this would be the parameterization for the arc f of gamma, right? So we're sort of parameterize this by wt. Okay? And so we want to understand properties of this new arc that we're defining, depending on properties of z and properties of f. Right? Because this will allow us, right? If we understand how a map f affects lines in a space, we're really understanding how it affects the whole space, right? A very good way of visualizing what happens to a space is if you make a grid on it and you see how the grid moves, right? You've seen, there were on the forum some animations even for some of the linear transformations over the Riemann sphere, right? They all use the fact that you put some grid in space and then you do some kind of transformation and you see how the grid is affected and how it moves or how it gets transformed, right? A grid is just one such line, right? Or many, of course, but if you understand what happens in an arc, you can understand what happens on the grid and so on. Okay. Okay, so let's say now that f is also analytic. Okay, so we have that f in analytic. Then it's very easy by just basically chain rule to understand what the derivative is, right? Essentially just chain rule, right? Then the derivative of w at some point t, right, is just given by the derivative of f at the point z of t, right, times the derivative of z at point t. Right? Okay. Okay, let me erase over here. Okay, so maybe before I erase this, let me just say a couple of words, right, since this is in the homework. Right, if you recall the proof of when we showed that a function only takes real values and is differentiable, is analytic, then it must be constant, right? What we used was the Cauchy-Riemann equations to make sure that if the function only took real values, then it needed to be a constant, and all these exercises of doing for each one of these are of that style. Right? For argument and no modulos, you need to be a little more clever in how you set things up, but the real part, imaginary part, is exactly what we did for the real valued functions. Okay. Okay, so now something interesting happens. And I think this is yet another interesting, surprising thing that happens in complex analysis. Okay, let's say, or let's set t0 such that f prime of t0 is not 0. Oh, f prime of zt0, sorry, of course. Right, so let's set a curve, right, z at a point t0 that's going through a point where f is not 0, right? So I have z, right? This is z of t. Maybe here, or let's say here, is z of t0, right? And in this point, the derivative of f is not 0. Okay. And let's say also that, you know, if the curve is regular, this shouldn't happen anyway. But let's just make sure that the parameterization isn't sort of silly, right? That it doesn't have derivative 0 there, right? But if the parameterization, the path is regular, this will always happen for all points. So, you know, asking for this is not as stringent. Asking for this is a bit more. But let's say that we're in a point where the derivative is not 0. Okay, then because of this formula, right? If it's not 0, then the argument of this number is just the sum of the other arguments, right? And the argument is well defined. So we get this sort of amazing equation. I mean, it might not look like much, but we'll take a few implications out of it. Okay, that the argument of the derivative at the point, at the new arc, at the point t0, is equal to the argument of f prime at that point, z of t0, right, plus the argument of z t0. Okay, so this might, you know, not much happened. We just took chain rule, and then we took, you know, we assumed that these numbers weren't 0, and we took arguments, and we used the fact that the argument of the product is the sum of the arguments. But now something very interesting happens, right? Because let's say that I have indeed a curve. You know, let's say that I have a curve z. I'm going to be a bit, you know, a little bit of abusive notation. I'm going to call this the curve zt, like as we are used to calling a function, like the function x squared, right? And let's say this is the point t0. Okay. And now, right, we apply f, and we go to some other, or I should say z of t0. Right, and now we apply f, and it's some other curve, or a w. Okay, and maybe this is w of t0. But now let's say that I have a second curve. Okay, let's say that I have, let me instead call this z1, w1, w1, and let me make another green curve. Right, so this is some other curve. Maybe green, can you see the difference? Maybe I'm looking in the video, and the green is not the best choice of color, it seems, because it seems quite similar to the white. So let me use purple. Maybe that's better. Yeah, I think that looks better. Okay, so I have another purple line. Let's call this z2, right, of t, and let's say that it's the same point. I mean, just to be. I mean, of course, this doesn't need to be. You know, the parameterization doesn't need to be so that the t0 is the same, right? But maybe I should not confuse. I should just put some other point. Okay. Now this will go to some other curve, right? Who knows what this curve looks like, right? The z, you know, w2 of t will be, say, f of z2 of t. But what this tells me is that the angle, right? What is this angle here? Right, the tangent at t0, right? The angle of this vector, the tangent at z of t0 is given by the argument of the derivative, right? Because the derivative points in the place where the curve is going. If the curve is going, say, this direction, right? Then the argument of the derivative tells me exactly what is the angle of the tangent to the path, right? But now, if I do the same thing for the purple one, right? And now I have some other tangent line at the same place. What this tells me is that the angle for the tangent line after the image, right, is whatever was the angle before plus something that depends only on the function. So in particular, if the curves were tangent before, they need to be tangent still now. Right? So this maybe is W2 of t. And the point is that if they were tangent before, they need to still be tangent now. Right? So the effect that this function, this mapping has on space keeps tangent lines, tangent arcs still tangent after you take it, right? After you take the mapping. Okay, so let's maybe write that. This might not, this might not yet look super surprising, but give it a minute. Okay, so F takes tangent, let's say F analytic. Okay, let me be a bit more precise maybe. Okay, so we take F analytic, right? And some point Z0 such that F of Z0 is not 0, right? If it's 0, then there's not much we can say, right? Because then this argument doesn't work. Okay, if F is analytic and Z0 is such that this, then F takes tangent arcs in Z0 to tangent arcs in FZ0. Okay, this might not look like much, or I mean, it's doing, might not look that surprising. But here's the other thing that I would say is perhaps more surprising, and it comes exactly out of the same equation, which is, let's say that instead of tangent lines, okay, let me attempt to again draw some lines. Let's say that instead of tangent lines, I had arcs that go through a point Z0, whose tangents had a certain angle, right? Some angle alpha. Right? Then, the angle between the curves, right? The tangents of the, angle between the curves, I mean the angle between the tangents of the curves. Before you apply F, right, gets changed by a certain amount, but it's an additive amount, and it's the same for any, right? It doesn't matter what the curve is. All that it depends on, the change that you see on the angles, all it depends on is the derivative of F at the point, right? And so this means that when you apply F on two curves that were at a certain angle alpha, then their image will also need to be at the same angle. Let me see if I can... so I need to make sure that... Yeah, okay, you have to imagine these angles are the same. Right, because, the curve, the angle from the curve, right? So here we'll have a certain angle, and now here we'll have another angle, right? But the difference between these two angles is given by an additive factor that depends only on the derivative of F. And so each of the arcs tangent at that point gets rotated, but it gets rotated by exactly the same amount. It gets rotated by this, right? And so this means in particular that it's not only that F analytic and this, then F takes tangent arcs to tangent arcs, but actually F takes arcs at an angle alpha to arcs at also an angle alpha. So locally, this mapping keeps the angles between lines. And if you think about this, this is a lot more surprising. At least I feel it. When I first saw this, it somehow feels a lot more surprising. Okay, I just saw someone wrote. I'll make it. Yeah, I'll write it a bit better. So F analytic. And wait, let's see if I. Okay, I'll just rewrite this because the issue is if I erase something on the top, then it well does this. Okay. So I need. Okay. All right. I'll just rewrite the theorem now. Right, so basically what we proved, I mean, right, to actually write down a proof, all you have to do is take two paths, right, and take the image of the two paths, and when you subtract, this term cancels out, right? That's literally all that goes on. Right, we have a theorem. Okay, let's say, I'll write here in a bit more, okay. C, right, and so F analytic, and Z0 such that f of Z0 is not 0, right? Then f takes tangent arcs at 0 into tangent arcs at fz0, right? Because if the angle is the same, when you just add a constant that doesn't depend on that angle, then of course it will be the same, right? But moreover, f takes arcs at an angle like theta for any theta, two arcs at the same angle. Same, I mean angle as in relative angle. Takes, yeah, okay, I should write here, takes two arcs. Because, right, I mean the angle between them takes two arcs at a relative angle. Okay, and picture, it's nothing like a picture. Right, so if I have something like this and something like this, all right, and I have some angle theta, let's say, then f will take these two curves to some other curves. Doesn't matter what they look like, but such that the angles will be the same. Okay, so let me see if I can make them. Right, where this angle will also be theta. Okay, so this we call a conformal mapping. So maps that keep the angles, right? Maps of the plane that keeps the angles, right? So this we call a conformal map. Right, so conformal map is a map from the plane to the plane, or okay, someone is asking why is it that follows that angles are the same, right? So take two curves. Okay, I mean we can do it, right? So take a curve z1, right, at the point z0, right? To make things simpler, I'm gonna parameterize the two curves, just so that maybe this is a bit. Okay, I'm going to take two curves and parameterize them in a way that they are the same at the same parameter t0. Of course, I could parameterize them in whatever way, right? But I'm saying that this, right, there's a curve z1, say, and there's a curve z2, right? And z0 here is a point, not a curve. And this happens to be the place of z1 t0 and z2 t0. Of course, there's no reason for them to meet at the point with the same t0, but I can just, I can just reparameterize for that to happen, so I don't have to worry about such things. Okay, then okay, so then the angle, right, and then f, right, when I apply f, so right, f of Z1 T, I'm calling it W1 T, right? This is the new curve. And f of Z2 T, I'm calling it W2 T. Okay, so now let's just apply that formula, right? If I look at the argument, right, the relative angle between W, right? So W prime, right? This is the angle of the, right? This is the angle of the, there is a typo here, right? It's the derivative that's non-zero, of course, not the function. Okay, so now if I want to look at the relative angle here, right, of the curves W, right, then I have to look at the argument of W, say 2, right, at some point T0 minus the argument, right? So the argument minus the argument of W1 T0, say, right? Remember, they are, right, since these points are the same, W1 T0 and W2 T0 are also the same. So I'm looking at the angle between lines that come out of the same point, right? But what is this equal to? Right? I just have to use that formula. It's equal to the argument of f prime at Z1 T0, right, plus the argument of Z1 prime T0, right, minus this again, but now at the point Z2 T0, but these are the same points, right? So this term is the same as that, minus again the argument of Z2 prime T0. Right? All I'm using is this formula here, right? I'm just using this, right? Okay, but now we're done, right? Because, you know, this is the same as that, so I can cancel, right? There's a minus here, there's a plus there. I can cancel this out, and I get that the relative angle between the tangent lines at W2 and W1 is the same as the one between, of course, I swapped the ones and the two, sorry. Not here, it doesn't make any difference, of course, but okay, better to be correct, right? The one with, right, the relative angle on the images between the second curve and the first one is the same as the one between the right, the image, the pre-image of the second curve and the one and the first. Okay, is this clear? Yeah. Okay. If not, please, yeah, go ahead, ask, mute yourself, and okay, but just follows. I mean, right. Maybe even easier to see than the formula. It just follows from the fact that what happens to the tangent lines of arcs is they get rotated by a fixed amount, a fixed angle, where the angle is exactly the derivative of f at that point. And so if you have two lines at a certain angle, they get rotated by exactly the same angle, right? If you have, say, two lines, right, and they get rotated by the same angle, then, you know, their angle will be the same, right? That's all this formula is showing, right? Okay, so this we call a conformal map. Okay, now let me, there's a few things I can or would like to say. I might have to prioritize. Let's see. Okay, yeah, we have time. Okay, so I'm going to erase this. So maybe before exploring a bit more properties of this mapping, let me give an example. Okay, so a very natural class of examples to study are the linear transformations, right? So we talked about them a little, right? You could study, right, examples just to get a better feel for what's going on. You'll see a lot more examples in the exercise class and through the homework and so on, but maybe since it's a good time to just see, one at least. Right, so one good example is linear transformations, right? We saw these objects a lot in like a few classes ago, and it's a very good sort of function or transformation to have in mind to see, to get a sense and visualize some of the things going on. Okay, so the book, for example, has maybe a section all about trying to study this example, and so I highly recommend taking a look at that, and you'll do some of that in the exercise classes. Let me look at a different example, right? Not one that's one of these transformations that's naturally viewed in the Riemann sphere, but let me take instead, right, the exponential. Okay, so let's look at this example, the exponential, and let's see what happens. Okay, let's look at what the exponential is doing, say at 0, for example. Right, so I take, this is my point 0, say this is my point 1, this is my point I. Okay, and now I'm going to apply f, right? I'm going to do f, right? F of z, just the exponential of z. Okay, and see what happens, right? So let's see what happens to these two curves. So let's say I take this arc, right? Where do the reals get mapped when I hit it with the exponential, right? The exponential of a real is real, so they get mapped exactly where where they were, right? And in particular, 0. Let's say 0 is our main, right, the main player in this game, right? 0 gets mapped to 1 basically, right? X of 0. Which is 1. Okay, but now where do the complex line, right, the complex axis, the imaginary axis, where does it get mapped? Right, it get mapped, right, to places, right? So if I have, maybe I'll do this, right? If I have some, say, y, I, right, it will get mapped to exponential iy, right, which we know is just a circle, right? It just gives the circle, which means that the pink line gets mapped to, let's see, so let's say 0 is here, and no, -1 here, and like I, right, simply gets mapped to the line, right? So the x-axis or the real axis gets mapped to the real axis, the imaginary axis gets mapped to the circle. And now if we're going to investigate what happens at the point, right? This is the special point, right? The tangent lines, their angle is 90 degrees, right? They form a right angle, right? So there's here. Right? It just so happens that the right angle is exactly the same. If I had done another point, it could have been that I would have seen a right angle like this, right? I mean, of course, but it is a right angle, right? And so this is an example where you see exactly the same angle, right? And you can go and study it in every pair of curves on every point, because the derivative of the exponential is never 0, and you're going to see that it keeps all the angles the same. Right? And also a cool thing is it's transforming, right? It's transforming lines into circles. Right? And now, sort of just as a bit of a teaser of what's to come, you can now ask, okay, so what's going on with, right? What's going on? How are the regions being transformed to each other if I take a region? And in particular, what happens, say, to this region? Right? Where does this region get transformed? Right? And we see, it's not so hard to see that this is the exponential of numbers with negative real parts, right? And so it'll get transformed to inside here. Okay, and so I won't get much into it for now, but now you can start asking questions of which regions can we map into other regions with conformal maps, right? With maps with maps where the angles are all kept, right? To study that, this is maybe not the best example because, you know, it's easy to define the exponential. When doing the logarithm, we get into trouble. We have to be very careful. But just to give you a hint that, right, these maps also take regions to other regions, and this is much, much nicer viewed with linear transformations. I highly recommend just trying to draw an example, and it motivates the question of what regions can we map to other regions where we keep all the angles the same, and this in fact is one of the main results in complex analysis, depending which direction we take in the end, which is called the Riemann mapping theorem, which basically says that under certain conditions, any region can sort of be mapped to any region, where any is regions that satisfy certain properties. Okay, this is one of the big, theorems in complex analysis, which we may or may not have time to reach, depending which path we decide to take. But just wanted to now sort of give you a teaser of something that's to come. We'll definitely talk about it, even if I'm not sure we'll prove it. Okay, so now another thing we can study, right, of what happens when we map. Okay, so let me in the last 5 minutes just say two things. One is we can study what happens from an analytic function, right? Analytic. Right? What happens if to the size of these tangents, right? If I can ask now what happens to the size of the derivatives, what happens to the if I have a path, do I stretch the path or do I contract the path? And that's not so hard to see, right? Because if we look at, say, the limit of z going to some point z0, for this we don't even need to define arcs for now, right? And I look at, say, the distance between fz minus fz0, right, divided by the distance before I do the image, right? So I take a point z0, and now I'm approaching it through some point z, right? And now if I look at what's happening through this map, right, on the other side, I have a point f of z0 that I'm approaching by f of z. And now can I ask, how does the speed of approaching vary, right? This is exactly what this is capturing. But I mean, we know, right? I can push the absolute values outside of everything. All this is, if the function is analytic, is the norm of f prime z0. Okay, so this tells us yet another theorem, right? That analytic. This not good choice of color. Sorry. Right, analytic functions right expand or contract the space around a point say z0 by f prime z0. Right, the cool thing here is there's two cool things. One is independent. This is independent of direction. Right, you could imagine maps. I mean, when we're talking about real analysis, we can definitely imagine maps where I just shrink, say, the imaginary part. Right, if I grab the function that just halves the imaginary part, is definitely shrinking the imaginary part very differently than it is shrinking the real part. Right, and so that such a thing just cannot be analytic, right? Independent of direction, but it might depends on the point, right? In different points, it will shrink and it will expand space differently, of course. Again, this is very easy to see here, right? Because the exponential definitely expands space a lot more once you're far away from zero than when you're very close to zero. Okay, so now there's just two things I want to say in the last 2 minutes. So maybe I won't do a full proof, but I'll just say them. One is, and I'll leave this as a nice homework, just think about it, which is that now I can ask whether such things have a, there's two things I can ask that I think would be very natural questions here. One is, can I ask whether I can actually prove something like this, looking at lengths of lines in integrals and so on. And in particular, if the space is being expanded by this amount, it definitely suggests that the area should be expanded or contracted by the square of this. Right? And so an exercise that I think will take you a few minutes and is worth doing is just try to show that if you have an infinitesimal space like say region around the point, that its area infinitesimally will be contracted or expanded by the square of this. Right? And basically what will happen is, if you think of it as a map from R2 to R2, right, the area should be affected by the determinant of the Jacobian, right? But what is the determinant of the Jacobian? We saw actually back in maybe even the first or second week, right, that essentially you get like the partial derivative of u with respect to x times the partial derivative v with respect to y minus the cross derivatives. And because of Cauchy-Riemann equations, this was exactly this squared. We actually even saw this maybe in the second week, right? And so this is something that tells you, that this at least is compatible with, like, if you were to look at this with real analysis. The other thing that now I don't have time to prove, and I really want to start integration next week. So I think I'll just skip it, but you should try to do it at home, is there's a very natural question now of whether there is a converse to all of this. Meaning, if I have a map that's, say, differentiable as a real map from R2 to R2, and is also conformal in the sense that it keeps all the angles, can I prove that it's actually analytic? And so it turns out that you can, and this is an excellent exercise. I mean, it's in the book, but just try to do it yourself. Try to prove that if I have a function from R2 to R2, say with derivatives, say continuous derivatives if you like, and I'm not so worried about what's the smallest amount of regularity you need to enforce or anything like this, and such that the angles are kept, and try to prove that it needs to be analytic, right? What are you going to do? You're going to try to make the Cauchy-Riemann equation show up. Right? Now, another word is that you could also ask the question of, would it be enough to have something like this, right? If instead, like if I just ask that the map expands and contracts around the point in a way that does not depend on direction, is that enough to force the function to be analytic? Okay, so think about this, and maybe I'll give the answer at the beginning of next week. Again, all this stuff is, of course, in the book, but just try to think about it for yourself first before looking, right? So which are converses to both these things that we did today, and which one is true, which one is not, or if both are true or both are not. Okay. All right. Thank you. Sorry for the extra minute. I'll stick around for a bit if there's any questions.